Okay, so now that we know how to describe the second Taylor polynomial, we're going to use it um, to find a quadratic approximation for the function f of x equals the cosine of x. This problem actually asks us to find a bound for the error using that Taylor polynomial, second Taylor polynomial. It gives us a base of 0 and it gives us an interval to work on. But in order to find that error, it's useful to do a couple of things. One is to find that second Taylor polynomial. So let's start with that. T sub 2 is equal to the same as T sub 1. We start with that, f of b plus f prime of b times x minus b. And to that, we're going to add 1/2 f double prime of b times x minus b quantity squared. Now, we know what b is, 0. We're given 0, so I'll plug that in here. I'll just write it that way for now. And we can tell what f of 0 is, f prime of 0 is, and what f double prime of 0 is. Well, almost anyway. First of all, we need to know that since f of x is the cosine of x, f prime of x is negative the sine of x, and f double prime is negative the cosine of x. So I know by looking at f of 0, if I just plug 0 in for my original function, I'm going to get cosine of 0, which is 1. I'm also going to get, when I plug 0 into f prime, I'm going to get sine of 0, negative sine of 0, and that's 0. So I'll have plus 0 times x, and then plus 1/2 f double prime at 0 is negative the cosine of 0, or negative 1. So that gives me negative 1 times x minus 0. That could have been a 0 up there as well, since I know what b is, right? X minus 0 squared, and that's 1 minus 1/2 x squared. If you graph cosine of x between, say, negative pi over 2 and pi over 2, it will look something like this. If you graph this quadratic, it will look something like this. I'm exaggerating a little bit, but you get the idea. This is my t sub 2, whereas this is my f of x. They're very similar. In fact, my graph, my sketch here really does not do it justice. Let me see if I can get a broader pen or something. The quadratic actually really quite closely mimics the cosine curve for quite a long way. So that's a terrible graph, but I hope you get the idea. The approximation given by 1 minus 1/2 x squared is really quite close for a reasonable amount of the x-axis, a reasonable range of values between, maybe there and there, right? Somewhere in here, that the approximation given by 1 minus x squared, 1/2 x squared, is good for cosine of x in a pretty decent range of values. Now, if we went to a cubic, the approximation would be even better. But that's not the point of this video. The point of this video is to find the quadratic approximation for cosine of x on the interval negative 0.2 to 0.2, and then to find the error given by the second polynomial, the error given by this over that interval. So let's do that part next. We'll start by recalling that our error is given by m over 6 times x minus b cubed. And that's because we're working with Taylor polynomial 2, the second Taylor polynomial. And we know what b is in this instance. So our error is going to be m over 6 times, I won't bother to write it as x minus 0, I'll just write it as x minus 0 is x cubed. And we have to figure out what m is. M, in the first Taylor polynomial, m was the largest value that the second derivative could take on. In the second Taylor polynomial, m is the largest possible value that the third derivative can take on. Well, we haven't computed the third derivative yet, but it's easy enough to do that here. The third derivative of cosine is the first derivative of negative cosine. So that's going to be negative. The derivative of cosine is negative, so we get negative sine, or I'm just going to write it as sine. Now we take a look at this function, the third derivative of f, this function, and say, what is its maximum value? Well, it's 1, right? So that means that m can't be any bigger than 1. Our error is going to have to be something less than 1 over 6 x cubed. So we now know what the error is likely to be in relation to x, but what values can x take on? Well, we're given this interval here to work with, right? So again, if we take a look at our function, f of x equals the cosine of x, I'll just graph it quickly here. Not a good graph, but we'll do something like this. And we're interested in this graph between negative 0.2 and positive 0.2. And that's actually really quite a small interval around 0 here. It's actually even smaller than that. My scale is way off here, but I think it illustrates we're really only interested in this function for a very small window. And in fact, if you graph both the function and its second Taylor polynomial, you'll see that in that particular interval, that the approximation that this is given by the Taylor polynomial is pretty good. But it's not going to be perfect. It's only going to be perfect at 0, right? That's our b value. B is 0. Notice that at 0, both cosine of x and 1 minus 1/2 x squared have the same value. When x is 0 here, cosine is 1. When x is 0 here, the value is also 1. Well, since what we want is for our error to be less than this quantity here, what we're going to be looking for is what is the largest possible value the right-hand side can be. So what we're saying here is our error is guaranteed to be less than something. What is that something? We're not trying to set the error in this case. We're trying to find out what the biggest error is. And then we can say that our error will always be smaller than that number. So what is the biggest thing that the right-hand side can be? Well, x is cubed here. So if you take a look at this function, at this graph right here, you get, see, I have the wrong pen size and everything here. You get something that kind of looks like this. And if you restrict that from negative to positive 0.2, you can see that the piece of the graph we can use for our purposes here is just that part right there. The very largest that this function ever gets, that x cubed ever gets, occurs at 0.2. So when x is at 0.2, x cubed will be as big as it can get in that interval. And if x is 0.2, gives us the biggest possible value for x cubed, then our right-hand side is as big as it can be. That tells me that this error has to be something less than or equal to 0.2 cubed over 6, which is, well, I'll say approximately 0.113, 0.11, no, 0.00, let me fix that, 0.0013 repeating. And your course pack gives that as 0.0014. I'm not sure why they round up there. Probably because we're trying to identify the largest possible error, right? We want to know what is the largest possible error here. If I round down, then there's a very unlikely, only happens way out of the very extremes of the range of values, but there's a situation in which we could have an error larger. I'm talking about if I erase the repeating bar here, right? This value here is smaller than this value here. This value here is not completely accurate because the actual error has a 3 repeating at the end here. But if I just round to the 0.0013, then what if I get an error that's 0.00131, right? That's still under the 00131 repeating, but it's bigger than 0.0013. So I think your course pack, the author of the course pack has rounded up to account for that and just give you 4 decimal places or 4 significant figures so that you can be absolutely sure that the error we're looking for, the value that we're going to be certain about in our error computation is that error will always be less than this value here. Now, your textbook makes another observation here, your course pack rather, and I think it's quite an interesting one. If you notice that the third derivative, the sine, is the sine function, right? And you look at that sine function between negative 0.2 and positive 0.2. Again, I'm exaggerating. The range of values is actually much smaller than this, but we'll go with that for now. We'll say this is 0.2. And then you can notice, you can observe that the y value here, especially between 0 and 0.2, it's a little more obvious there. The y value is always less than the x value. The sine is always less than its input. Now, after 0.2, that's no longer true, but between negative 0.2 and positive 0.2, the absolute value of sine is less than the absolute value of its input. That lets us write something like this. Sine of x is less than or equal to x on the interval negative 0.2 to 0.2. And what that tells us is that the third derivative never gets any bigger than 0.2. So I could instead have used 0.2 here instead of 1. And that would have yielded, I'm going to put a times, that would have yielded an error of 0.00027, which is even smaller, considerably, than the previous value. So that's an observation that you might have been able to make. It's not something necessarily that you can just compute. It's one of the reasons that mathematics needs to be about more than just formulas and computations, right? We need to be able to think critically and analytically about a situation. I'll be honest, I don't know that I would have noticed that. I took it out of your course pack, but it is the kind of thing that you want to be able to observe. For example, like noticing that the 6 in the denominator of a problem we were working on here, actually I described it in the previous video, can be thought of as 3 factorial, that kind of observation. Anyway, so here's an error estimate for this example. We found the Taylor polynomial, and we found a quite adequate error estimate for it as well. For the record, the course pack says about this observation to see page 212 in Stewart. If you manage to get your hands on a copy of the Stewart calculus textbook, you'll probably find that there's no reference to this on page 212. And I suspect that that's because this course pack is considerably older than the current edition we're using for, that anybody is using for the calculus textbook. And welcome, we don't use Stewart at all at the moment, but depending on when you're actually watching this video, that could change as well. At any rate, if you don't find it on page 212, you may be able to find it elsewhere in the book, but it's not on page 212 in a current edition. Okay, let's take a look at another example. Let's find the second Taylor polynomial for f of x equals ln of x, based at b equals 1 on the interval 0.8 to 1.2. Now, from previous experience, I would say it's pretty safe to say that we know we're going to want a bunch of derivatives. Let's rewrite our function, its first, second, and third derivatives out here. If you can't find or don't know where I got these derivatives, take a quick moment and remind yourself how to find them. That's not the fourth derivative that I want, it's the third. Let's try that again. That's what I get for trying to talk and write at the same time. There we go. Those are the first 3 derivatives of f of x. Our formula for t sub 2 is equal to f of b plus f prime of b times x minus b plus f double prime of b times x minus b squared. And we know what b is. We're given b equals 1. So I could write that as f of 1 plus f prime of 1, but I'm actually going to go ahead and dive into the values here. If I evaluate each of these at b equals 1, I'll get 0, 1, -1, and 2. So f of b is 0. F prime of b is 1, so I'm going to have plus 1 times x minus b. Well, b is 1, so I can replace that as well. Plus f double prime of b, well, that's -1, so I'm going to have minus 1 times, actually, I've left something out of my formula here, so let me correct that. This should be plus 1/2 f double prime of b x minus b squared. So I'm going to have plus 1/2 times -1, -1 being my f double prime of b, times x minus 1 quantity squared. And that simplifies to x minus 1 minus 1/2 x minus 1 quantity squared. That's my second Taylor polynomial for y equals the natural log of x. If you graph these, you'll see that that's a pretty reasonable approximation. Around 1, it fairly quickly degrades, and the approximation is really no longer very good. But for what we were asked to do, we found the second Taylor polynomial, and we're going to use that now. I didn't write this down. We're going to use that to find the error. Okay, so there's our second instruction written out there. We're going to find the error bound for the second Taylor polynomial for ln of x on the interval 0.8 to 1.2. The natural log function looks something like this, and the Taylor polynomial looks something like this. It actually comes outside the graph of the log over here, but it's inside for the rest of it. What we're looking at is really what's going on kind of in here, in this region here, right? So what we want to know then is what is E? So E is something less than or equal to m over 6 times x minus 1 cubed. That's E sub 2. And that's equal to, let's put over 6 and x minus 1 cubed in here, and let's see if we can figure out what m is. Well, m, remember, is the largest possible value the third derivative can take on. So if you look at the third derivative here, it's 2 over x cubed, and that looks something like, where's my pen? It looks something like this. 1 over x looks like this. 1 over x cubed looks like this. 1 over x to the 5th looks like this. Of course, they're stretched differently, but they all look vaguely like that. And then, of course, the 2 stretches it a slightly different way. And what we're looking at is between 0.8 and 1.2. Where is this thing at its maximum value? Well, it's at its maximum value at its left endpoint, 0.8. So that means that since what I'm looking for here is m, the largest value this function can take on in that interval, that's going to be this function, this value right here. What is 2 over x cubed when x is 0.8? I'll grab my calculator here, and I have 2 divided by 0.8 cubed is 3.9. So that's going to be it's 3.90625, so it's 3.91, but I'm just going to put 3.9. Especially since what we want is for the error to be less than this, we want to tend to use the biggest possible values we can here. So it might actually be beneficial to round that up to 3.91. Okay. Right, so now we know what m is, but we're still trying to figure out that our error is going to be less than this quantity. That means this quantity here has to be as big as possible. So let's take a look now at what this thing looks like. And that's a cubic graph. It's going to look something like this. Shifted to the right 1 unit and scaled. It's a terrible graph, but you can see where this thing is at its largest. It's at its largest it's going to be at its largest, its farthest endpoint. If that's 0.8 and this is 1.2, the largest value this thing's going to take on is there. So I'm going to plug 1.2 in for my x here, and that's going to be, so I'll have 3.91 over 6 times 1.2 minus 1 cubed, and that works out to be 0.005213 repeating. 5213 repeating. So in the same sense as we kind of rounded up last time, let's round up this time as well. Let's call that 0.0053. And that means that we have found an upper bound on the error for this function using this Taylor polynomial to approximate it on this interval. Let's take a look, though, at what happens if we change the interval just a little bit. This doesn't seem like much of a change, but as you'll see in a moment here, it's going to make a huge difference to the error. I'm not going to bother with the Taylor polynomial because none of that changes. I've found an approximating curve. That's all that really matters there. I'm still centered or based around x equals 1, so these values all stay the same. So all I really need to do is change my function in here. And the function I'm going to, or the values that I'm going to change are not, nothing to do with the formula. The 6 stays here. Remember, that's just 3 factorial. What I'm going to do is change the 0.8 here that I used to compute 3.91. I'm going to use 0.5 instead. And here I'm going to use 1.5. So let's make that quick change. That was an easy one. Call this 1.5. We get different values here. And this value here, when I change the value that I use to compute m, let's go back to what we did there. M is the largest value this can take on. What is the largest value 2 over x cubed can take on this interval? Well, here's my 2 over x cubed, so it's going to happen at 0.5. So 2 over 0.5 cubed gives me 16. That's a pretty big difference. I had 3.91 and now I have 16. So 16 divided by 6 times 1.5 minus 3 is 1.5 minus 1 cubed is 0.333. 3 repeating. That's a huge error, right? And that's interesting because you can see I changed my interval here by only 0.2 on one side and 0.3 on the other. So by changing my interval by only 3/10 of a point here, I changed my error by, well, by a lot, right? I went from 5 1/1000ths to 3/10, more than 3/10. So that change in the interval made a huge change in the amount of error. If you graph the functions y equals ln of x and y equals this polynomial here, this Taylor polynomial, you'll see that they're not really all that great of a fit, right? The Taylor polynomial is not the greatest fit for the natural log. And that's because the natural log isn't a quadratic behaving function, right? Sine and cosine kind of look like little quadratics, you know, one next to the other, one upside down and one right side up and so on. Natural log doesn't behave like that at all. The natural log is going to require, in order to use an interval like 0.5 to 1.5, it's going to require a much higher degree of Taylor polynomial. We only went up to degree 2 here. For now, though, we have learned how to find the Taylor polynomial for a function, a couple of different kinds of functions, and how to use the error bound formula to find the error associated with that Taylor polynomial for that function.